Hi everyone, I'm Emilie Cloos and I'm the Loans and Exhibitions Conservator within the Collection Care Department at the National Archives. Today I want to briefly introduce you to microfading, what it is, how we use it and why. Working in loans and exhibitions, I spent a lot of time looking into light management. Light is this necessary thing for everyone to see our amazing collection, but it's also one of the main agents of deterioration. So we strive to find a balance between access and the preservation needs of our documents. But how do we do this? The National Archives have a lighting policy which contains light sensitivity categories, as you can see here. When we want to display a document, it gets assigned a light sensitivity category, and with that, a light budget. That is, how much light it can receive per decade. We know our collection items are not forever, but we try to manage their lifetime by aiming at not exceeding one just noticeable difference per 50-year period. A just noticeable difference marks the point at which a change will be visible to the naked eye. So far, so good. But we don't always know for sure what something is made out of and how certain media, certain colorants, for example, will react to light in real life. That is where science comes to the rescue. We have in our lab in collection care a scientific tool called a microphotometer or microfade tester. Microfading is an accelerated light fading method that will allow us to predict how a collection item may change when exposed to light during an exhibition. Here you can see what our machine looks like. Our setup is retroreflective. Light travels from the light source, which is here, to the probe, which is on the right here, via fiber optic cable. The probe shines a very, very high intensity light, because we need reactions to happen much quicker than in real life, onto a spot on a selected document. And it collects what is reflected back via another fiber optic cable, and it's all recorded here in a spectrophotometer. Our light source is powered by 4 LEDs, each operating different wavelengths to replicate visible light. The technique is micro-destructive, as it will fade a part of the document, but the beam, the spot itself, is so small at 0.3 millimeters that, except in very rare cases, it cannot be detected with the naked eye. And this is why it's called micro-destructive rather than destructive. This here is what is emitted. This is what the light spectrum looks like when all 4 LEDs are turned on and reflected back by a white standard, that is a crisp, clean white surface. This is essentially what white light is made of. What we see here is the visible light spectrum. It comprises the 7 colors of the rainbow. And on either side of this rainbow, we have the UV range on the left and the infrared range on the right. These ranges where the spectrum flattened, the human eye cannot see. Our light source does contain some UV. It emits in the near UV range, which is why there's a spike here in what I like to call the Batman ears. It is important to monitor this because UVs are the most damaging part of light to our collections. Depending on which color we will illuminate with the microphotometer, the shape of the spectrum will change. So what do we measure with our microphotometer? Well, we'll record namely color coordinates like you would record a particular geographical location on our planet. We use the lab LAB, color space, which places a particular color within this 3-dimensional space here, based on 3 axes: L from light to dark, A from green to red, and B from blue to yellow. We will typically run a test with the microphotometer for 10 minutes, and the machine will take a reading of these color coordinates every single second. This allows us to look at where a color started and where it ended once it has been artificially faded or changed. Let me show you with an example. These are ectograph or office copies of telegrams received by the SS Burma from the Titanic. And they are in crystal violet ink. We have a lot of similar examples in our collection. Crystal violet was very widely used at the beginning of the 20th century. Crystal violet is made of an aniline dye, a man-made synthetic dye. It is well known that these dyes are extremely light sensitive. Despite this, we sometimes want to know a little more, record some evidence to aid with display decision making. So here, perform a few tests with our microphotometer. This shows some of the things we look at. The first spectrum in turquoise is the purple ink as recorded at the very start of the test. The dark blue line is the spectrum showing what the purple ink looks like at the end of our 10-minute test. Looking at the two, we can see where the colors started and where it ended by how much it's changed and how. The difference here is very notable. You can see the gaps here, here, and here. The purple ink has become lighter, less blue, there's a decrease here, more yellow, there's an increase, and less red. We also use what is called a delta E equation to calculate color change. That is, we calculate the distance between two colors, or in this case, the distance between the color coordinates of the purple ink at the start and at the end of the test. Note that the average color change here for this particular test was 7.32. I should point out that we compare the fading behaviors we record with the microphotometer to a set of references, the blue wool standards. These are wool samples dyed with colorants that have known behaviors and are ranked from 1 to 8. What we can measure with our microphotometer, and incidentally what makes the bulk of our collection, falls within the first 3 categories here. If you remember, the purple ink from the telegrams we looked at before showed a delta E, a color change of 7.32. Well, we consider that a media is equivalent to blue wool 1, which corresponds to the highest light sensitivity category when the color change reaches about 3. That gives you an idea of just how sensitive the purple ink is. It's quite literally off the scale. Here, the fading rate is expressed in graph form because, here you can see 4 different lines because, like with most scientific experiments, one has to run multiple tests for consistency. It's interesting to look at this because it shows how much a media fades, but also how its fading behavior is. Here, the lines are a constant upward slope. The fading is incremental and constant, but sometimes media fade very quickly for the first few minutes of a test, but then plateau. The fading slows down and stabilizes. This is important because in some cases, what is already faded fades much more slowly than a media that is pristine. It's very counterintuitive, but it may mean that something that is already faded can be displayed for much longer, for example. You can enter the LAB values we have seen earlier, these color coordinates, to look at the actual corresponding color, to see, again, where we started, where we ended. And there are several websites you can use to do this. It's a very quick and visual way to express color change. You may not totally be able to see here on your screens, but as we have established, the purple ink of our telegrams got lighter and less blue. There's a difference in these LAB values. So I hope you have enjoyed this summary glimpse into microfading. I should stress that this tool does not give clear-cut answers, but is rather a decision-making aid. We extrapolate predictions from the results it gives, but we always bear in mind that in real life things may be a little different. Light damage will be influenced by a whole range of factors, such as the lighting system in a particular gallery, the relative humidity, the temperature, what the substrate of a particular document is made of, its condition, its fabrication process. The microphotometer only looks at photochemical degradation in the spots we've tested. Again, it gives an indication rather than a definite answer, but it is a wonderful tool for the museum professional to help make display decisions, And most importantly, it can facilitate conversations between conservators and curators, for example. Thank you very much.